This is lecture 6 in an introductory course on electricity and magnetism. And in this lecture, I'm going to introduce the useful diagram known as a field line diagram. So this lecture has a single learning outcome. It's to be able to determine, that is to figure out and draw the field line diagram for a collection of point charges. In a following video, lecture 7, I'm going to describe somewhat how to determine field line diagrams for what is known as a continuous point charge, or a continuous distribution of electric charge, as well as to calculate the electric field around that distribution. So in order to show you how to gain this learning outcome, this ability, we're going to start with the field line diagram of a single point charge. In here, we're going to have reason to talk about going away and going into. This is, what I mean by this is direction. So it's really the direction of the field line. Also, something about the number of field lines being associated with the amount of charge of our point charge, and also something about the density of field lines being proportional to the strength of the field. If you look up on Google, if you just type in field line diagram as an image search, you'll come out with images that look really similar to all of these here. This is what I mean by field line diagrams. It's a sort of convention that a lot of physicists use, and everyone uses it the same way to understand the physics in the same way. So if you look back at my list here of topic pieces, look at this. The field line go away from positive charges, go into negative charges. Just as an example of what I mean by that, here is a positive charge, and you can see that the arrows point away. So this surrounding the charge is called the field line diagram, and the little red circle with a plus sign, this is just the charge diagram. It's the diagram that shows you the charge. But what surrounds the charge is the field associated with the charge. And what I'm showing you how to do today is to draw the field diagram. So here's a negative charge, and here is the field, and the field looks like it's going into the negative charge. This right here is the field line diagram of what's known as an electric dipole. And I'm going to describe how you come up with this field line diagram during the lecture today. So going back, that electric dipole that I just pointed to is it's because of a positive charge and a negative charge that are sitting somewhat close to each other, and we are looking at the net electric field that surrounds and is even in between the two electric charges, the 2 point charges. So that's what the second piece of the lecture is about. It's how to understand, or how to determine, the field line diagram when you have multiple point charges. And I'm going to allude to, or a central issue is, you need to think about the superposition principle first before you begin to draw your field line diagram. Also, it is somewhat of an art, and you should feel free, if you start the process of drawing the field line diagram and you discover that it gets confusing, then maybe you should scratch that idea and draw it slightly differently. So the last comment in this lecture is going to be about field line diagrams that are drawn when there are conductor materials present. And there is something that you need to learn how to include in your field line diagram when you talk about conductors. And what you have to include is the fact that the field is always perpendicular. So the field line diagram is always going onto or away from the surface of conductors in a perpendicular way. So field lines are always perpendicular to the surface of conductors. All right, so yeah, so let's do this.
So what a field line diagram does is it gives a way to communicate details about electric field. And the details that are important to communicate about electric field are its direction throughout space, or the space of interest, and also how strong is the electric field at different places in the space. So we need to come up with a way, or what I'm going to show you is how to encode or depict these details in a diagram. So I'm going to show you, so these are, for lack of a better way to describe it, these are encoding rules. These are similar to what's referred to as map legend, if you know anything about cartography. So yeah, so this is what we're going to concentrate on, and I'm going to give you lots of, or a bunch of examples of me doing the process of doing the encoding. So here we go. Field diagrams of positive charges. So positive point charges. So we need to think about direction and strength. So field diagrams of positive point charges. So here is one. I'm going to say this thing here is a positive point charge, and the field line diagram of this is simple. So I'm going to take one field line, and so this is the field line here, or a field line, but right now it seems to depict only the electric field on the right hand side. So I'm going to say also, well, there's field above the charge, and the field above the charge looks really similar to the field on the right side of the charge, because this point charge has quite a lot of symmetry. So the symmetry is, in this case, it's spherical. So there is this pattern, and I'm trying to depict this sort of homogeneity of the field distributed around the charge. Now the reason that I put outbound arrows on the field lines, so why am I putting the outbound arrows on the field lines? Can you see they just point away from the positive charge? It's because this is the direction of force on what's referred to as a positive test charge. So let's imagine that the central positive charge here is called capital Q, and the positive test charge is called lowercase q. So if I put lowercase q, say here, so this is lowercase q, I place it there, and what I'm doing is I'm imagining testing the strength of capital Q's electric field. And I find that the strength of the force is, say, this big. Right? And it also points outwards. If I was to push put this little charge Q here instead, we'd find that the force was like that. If I was to put the point charge Q here, though, it's closer, and the strength of the field is actually quite a lot bigger. So let me explain something. If this, in some sort of units, had the value 1 for the force on the charge Q, it's one amount of force at this distance away, and if I stay radially the same distance away, then Coulomb's law is not going to update the strength of the force. It'll still be strength 1, but its direction is radially away from the charge capital Q at this new location. So you can see the direction is different, but the strength is not. But if I say if I take the charge little q and I go to half the distance, then what I end up getting is an upgrade in the strength of the electrostatic force up to 4 times as strong, right? So code for strength, it's how close the field lines are together. Another way to say this is it's the local density of the field lines. So this little charge is sort of close into here, and if I sort of check the immediate area, it's not very far to get to the nearest nearby field lines. So I'd say that close in, the field lines are quite dense compared to far out. If you go out here, how far you have to go to get to the adjacent field lines is actually quite far. So you'd say this is a low density of field lines, exhibits a weak field strength, and close in I have a high density of field lines, so that's a strong place in the electric field. So the code for the strength is the local density of field lines. Right, and the arrows or directions are the direction of force on a positive test charge Q. So let's move on, and actually I'm going to just do it here. So let's imagine a different charge, though. It's a thing that's kind of very, very positively charged. So if this was just Q, let's imagine this charge being twice the charge. So remembering what we know about the electric field is proportional to the amount of charge in the problem divided by the distance squared away from the charge. So if I was to double the charge, I'm going to have to think about a doubled field strength everywhere. So if I want to double the field strength everywhere, and I want to describe this in a diagram, and the code for strength is the density of field lines, then to double the field strength, let's double the density of the field lines. So doubling the density, I have 4 field lines. It's really easy diagrammatically if I'll just double the total number of field lines. So instead of just 4, I'm going to draw 8. And you can see that closer in, the density of field lines is twice as dense as in the drawing up above. So this is how you encode strength, And what's more is its relative strength. When you're solving a problem and you want to draw a field line diagram, you really do need to, like, you'll be practicing building up these field line diagrams and sort of learning the art. So it is an art, right? And sometimes you just simply need to start over. Sometimes you get yourself into a diagram that it's too confusing, and it's you didn't really choose the right number of field lines to draw from the beginning, and you should just scrap what you're working on if you find that you think you could do it a better way, and just start it over. And this is what leads to having a lot of practice. Practice makes perfect. So you got to start putting in your 10,000 hours for this. All right, so let's move on and do negative point charge. So this is the field line diagram for a negative point charge. Same thing goes. Here is the negative point charge. So this is our charge. And in the earlier drawing, if I had Q, I just had these 4 field lines. Let me just use negative Q. So I've got a negative amount of the same charge. So the field is going to be equally strong. So I'm only going to depict 4 field lines. But if I use direction of field line is direction of force on a positive test charge, lowercase q, then the field lines need to be directed in towards the negative charge. So negative charge, so all the field lines are going to go into the negative charge. And if I had, say, a doubly minus, or actually, why don't we make it 4 times as negative? So this charge here is very negative. In fact, it's negative 4q. So looking at the earlier diagrams, here is the same amount of charge, but they are of opposite signs. So positive test charge is pressed outwards, and the positive test charge is drawn inwards in that case. In order to depict a diagram for a doubled charge, I used twice as many field lines. I just needed to double the density. So you can imagine if I want to quadruple the strength of the field everywhere, then what I need to do is quadruple the number of field lines. So this one takes a little practice, but it turns out that you can just sort of follow the same pattern. So this is what I mean by practice. So I'll start by drawing, these are the field lines of one of the negative 4q's, right? Here is the field lines of the second of the 4q's, and here is the field lines of the third of the 4q's, and here are the field lines of the fourth of the 4q's. So I quadrupled the density of field lines everywhere to depict the quadrupled electric field strength. Relative to the upper diagram. Let me show you something real quick. So positive charge, field lines emanate or leave from the positive charge. Here's the doubled positive charge, and I have twice as many field lines emanating or leaving the positive charge. In the negative charge drawings, the field lines are sinking into, right? So I've got the quadruple or 4 times as many field lines sinking into this 4 times as much charge. So what people like to say, people like to, this page has a lot of mark on it. So people like to do this. Positive charge, positive charge is a so-called source of field lines. And negative charge is a sink of field lines. So here's negative charge, and the field lines sink down into the negative charge. Here's a positive charge, and the field lines emanate or source out of the positive charge. So this is a diagrammatic encoding. All right. So let's move on and study what's known as the electric dipole. And I'm going to ask you to reflect on using the superposition principle to think about the net electric field of the dipole. Right? So let's think in terms of the superposition principle for a minute. So I'm going to draw a coordinate system. So let's say this is the x-axis, and this right here is the z-axis. And so in a right-handed coordinate system, I know I refer to this quite a lot, and I haven't really shown you what one is, but a right-handed coordinate system has the y-axis actually point back into the page. So the y-axis points backwards if the x is towards the right and z is up. The y-axis is back into the page. But what I'm going to do is set up a plus q on top. So that's a positive charge. I'm making it somewhat explicit. Another way to do this is to just say I'm going to use q to denote a positive amount of charge. So there is q on top and minus q on the bottom. So here's the thing. If you go along this line of symmetry, I guess it's sort of a line of symmetry, it's not really, but the idea is this. If I put a test charge here, right, so this is a little positive test charge, so little q is also bigger than 0. This is our test charge that I alluded to earlier. Little q is positive, capital Q is positive, so this charge and that charge have a repulsive interaction, and one of the forces on little q is this way, right? It's away from capital Q. But if I ask, well, what's happening to q from minus q, in this case it's going to be attractive, so the attraction arrow is here. And if you think about it a second, the distance that little q is away from capital Q here, let's call it r, and the distance that little q is from negative q is also r, because because of similar triangles, or this distance is the same as that distance, and this is the same as itself, of course, what I'll get is these two electric forces are actually of the same magnitude, right? And if I imagine little q being closer in, it will still be the same, but the forces will be stronger, right? And if I'm further out, the forces will be the same as each other, but weaker, because I'm just further away from the charges. But if you look at these two arrows are always going to add such that, so this is the down to the right arrow, and the down to the left arrow just gets added on of the same magnitude. What they're always going to do is have a situation where there is horizontal cancellation and vertical accumulation, right? So the net result is the net force on little q is down. So net force on little q is down. Only the vertical components of each of those forces survive the superposition principle. So you go and you do this, and you discover that if, as you wander q to different places, closer in and further out, you're going to learn, if you just do this math and think in terms of superposition, that the force close in is going to be quite strong, and the force further out is going to be quite weak. So if I go on the other side in the negative x direction, so this direction is the negative x direction, and I check it sort of symmetrically on the other side, you're just going to determine that that it's going to have the same strength if you're on the same distance on the other side. So you can see that the electric field is going to diminish as I go away from the axis of the dipole equally in the positive x direction or the negative x direction. And what's more is you can imagine going out the y-axis and also the negative y-axis, and you're going to learn that all of these arrows are only sort of radially dependent in the xy plane. So, but what about this? This is pretty cool to ask. What if I ask here? What if I put the charge there? It's going to be repulsive because of capital Q, but it's going to be attractive because of the negative capital Q. But you can see that the distance between little q and negative q is actually quite far compared to the distance to the positive charge capital Q. So that means that this attraction is going to be somewhat smaller. And the result of adding this arrow plus this arrow ends up being, you imagine taking this and you put it here, and what you get is an arrow that looks like this kind of. And the idea is if you just do this everywhere, it begins to take on a shape that kind of looks like, whoops, the following thing. Here's plus and minus. Can you see this? This is indicating electric field here being this way. And if you wander Q around, what you're going to find is that that little arrow kind of tilts and turns over and points downwards as you wander the test charge down towards the x-axis or the xy plane. That red arrow will flip, and then as you wander down, it's going to flip again and point at the bottom of negative Q. This is very interesting, and so you begin to draw out a picture that looks like this, where over here it points down, but over here it points up and to the right. See, up and to the right? And down here, if you check it, it'll point up and towards the left. Yeah, that's right. So up and towards the left, like this. And then close into the charge, we imagine the field lines being close to each other. So you can see that the field lines are close to each other, nearby the charge. If you think about it a second, in between the two charges, this is interesting, it actually must point downwards. But that's what we're getting everywhere on the xy plane. So it's down, and then it's symmetric for the negative x-axis, so the field line diagram needs to be symmetric. That is, this field line and that field line need to look the same, sort of mirror images. And this field line and this field line I meant to draw them more similar. But yeah, you can begin to see. So you can see that the negative field lines are sinking down into the minus. So this field line sinks down into the minus, but it emanates from the plus. Like I said before, the positive charge is a source of field lines to fountain out or emerge out of, and the negative charge is the sink for all the field lines to go. Yeah, so this generates the field line diagram. I showed you a Google image earlier, and you might go and compare what I show you here and how I arrived at it or thought about it in terms of superposition principle, right? Two charges, I always have two force arrows I have to imagine superposing, adding together, yeah, to arrive at something that, that has a really pretty sort of look to it. But diagrammatically, it describes direction as well as, I'm going to add a field line. So I'm going to go pretty far out because I know that the field strength needs to diminish. It gets weaker, so the density of field lines needs to become less and less and less, right? Very close to the charges is where the field line densities are going to be very large. All right, so that's the idea of drawing a field line diagram for multiple point charges. But let me show you one last multiple point charge field line diagram. So the following thing is not strictly a dipole, but is similar. And it's interesting to wonder, how do you draw a field line diagram for it? So here's the thing I'm going to try to depict for you. Here is a doubly charged, so it's like a positive charge, and here instead is a negative charge, right? So let's say this is, so we're going to use we're going to say that capital Q is a positive value of charge. So this down here is negative Q, and this is 2Q, and we're understanding it to be a positive charge. All right, so I'd like you to notice something. Let's say that the distance between these two things is a distance d. And I'd like to ask you, what if I took this thing and I imagined it as a little bundle and asked you, what is the net charge? The net charge of this little bundle is 2Q plus negative Q is just equal to a single Q. So what I'd like you to imagine is, what's the field line diagram for a single Q? A single Q, let's draw it, it's right here. So this right here is Q, and far away, the field line diagram looks like the following. I'm going to draw it in a funny way. I'm going to draw the field lines sort of diagonal. So very far away from this charge Q, the field line diagram needs to basically look like what I drew in the first set of pictures. So I just got field lines that emanate away, where the density of field lines decreases as you get further away. and the field only points away from capital Q in this very symmetric way around capital Q. So what I drew is essentially this earlier picture diagonal, right? That's all I did. So here the field line's continuing away there and there, right? So that's what it's got to look like far away. Far away means at distances that are really big compared to this small distance of separation. So I'm imagining very far away from this charge distribution. But close in, right? Close in, I'm talking about at distances from the charge distribution that are similar to D. So let's think about what this has got to look like. What it's got to look like far away is this. So the picture that I draw close in you need to be able to imagine it morphing into this drawing. So let's see how that could work. So this is a source of field lines. It's actually a source. Earlier I used this encoding. I got 4 field lines for a single charge, actually for the negative charge. So for the negative charge down here I had 4 field lines, but I'm going to imagine drawing them diagonally. So here it is. So let's go 1, 2, 3, and 4. They are all sinking down into the minus. And the 2Q, this thing right here, had 8 field lines, but I'm going to draw them sort of on the sort of like a rotated picture. So I've got, let's see, this is going to be tough to do very well. So it's like kind of close to each other, emanating, right? Positive charge is a source for the field lines. So here they come away, but I've got to draw 8 of them. So there's a 3rd one, a 4th one, a 5th one, 6, 7, 8. So I tried to do it sort of homogeneously, but you could tell I was having some trouble. But there's 8 field lines. So here's how this has got to work. So these field lines are close to each other here, kind of like a small angle. These field lines are sort of more splayed apart, more obtuse angle. So this small angle I've got to obey, and I'm going to just join these up. So the source of the positive charge is sinking into the minus in terms of this field line, and these are going to do the same thing. So here they go, like this. Now what about these 4 field lines? They're not just going to go off to the top, right? These field lines don't have negative charge to sink into, but I need to figure out where they go. So where they go is here. That's how they need to distribute in the rest of the drawing. So I'm going to take this one and imagine it going off to infinity in this direction, and this one goes off to infinity in that direction, this one, and this one. And very far away from this charge distribution, this is how they connect up. So this was a how to handle when the 2 charges aren't the same amount, which is what a dipole is. And you really are thinking about sources of field lines. If you have negative charge, field lines have to sink into them. And this is how you can knit field lines together and still have an overall picture, right, that makes sense. The net charge of this is capital Q, and capital Q far away has 1, 2, 3, 4 field lines that are sort of symmetrically distributed around the charge distribution. Close in, the field line diagram is complicated, but far away, the field line diagram is simple. That's the simple net charge field line diagram. Okay, so the last comment is whenever there is a conductor, the field lines must so whenever there is a conductor, the field lines, I guess, must dead end or emanate from the conductor surface perpendicularly. So perpendicular. And I'm going to try to indicate to you why. And the answer has got to do with, what is called free conduction electrons. All right, so imagine we have something different. And what I mean by something different is here is a conductor. Actually, scratch that. I always end up doing this. What if I have a conductor in the shape of a cube? So conducting cube, right? So a conducting cube, this thing. And let's say, for the purposes of argument, that there is electric field that hits the conductor in this direction, right? What if? So here's what happens. So a field line is an instruction for positive and negative charge to feel force. So in this little area of the conductor is positive and negative charge. Let's imagine that the conductor was electrically neutral, just for the purposes of argument. So this field line is going to look at these positive charges and try to press them away. And it's going to take these negative charges and actually try to pull them toward, backwards along the field line. Right? You can imagine these little pluses and minuses as little test charges. And so what happens very quickly is these little red charges, these little red free conduction electrons in this conducting cube, they can respond to this field line. And what they do is they accelerate, or they feel a force in the direction of that field line. So in this case, let's imagine it's an acceleration in this way. So they actually move in that direction. And so let's imagine what that does. So in this little space where I'm looking at the charge, this field line, actually, there is no reason for it to be different, so I'm going to leave it the same. But in the little 4 pluses, they're not allowed to move because they're not the conducting charges. But the little minuses do get to move, so they move down to the bottom and sort of close to the surface. So they kind of like squeeze in like this, right? And when they do that, we get to have, because of this new charge distribution that didn't used to be there. So the charge distribution wasn't there, and this was the electric field. But now there is this interesting dipole, so dipole is induced. And if you have this induced dipole, then that means all of a sudden I have new electric field. And so the electric field is going to have something of a shape like this. And this electric field has to be superposed with the electric field that was already there. So you superpose. And when you superpose this electric field and that field line, what you get is very quickly it converts from this to this, which looks like the following. So here's that little place where we have pluses and negative charge, 1, 2, 3, 4. The net electric field looks like this instead. And this is the sense in which field lines must always dead end, right? And when we talk about field lines, actually, we talk about the net electric field. The net electric field ends up being perpendicular to the surfaces of conductors, because conductors can induce small dipoles, and the dipoles will show up with their fields until the charge separation causes the net field to be unable to cause any more induced dipole, and that's really confusing. But yeah, so this is the argument. So I just mixed some concepts from the lectures. I mixed up conductor and the free charge. I mixed in dipoles and the field diagram of a dipole, and I also mixed in superposition principle. And I figured out a problem. So I used these concepts, right? I mixed up a bunch of stuff, and I could answer this question. It's got to do with the free conduction electrons, but if you just say, so if the question was why must field lines dead end or emanate from conductor surfaces perpendicular? And if you answered, well, it's because of the free conduction electrons, that's an incomplete answer, because you didn't show why it has to do with the free conduction electrons. And showing why involves modeling a conductor, right? I modeled the conductor and asked, what would a non-perpendicular field line do? And then I followed my nose and I showed how you could describe why a net field line is going to be perpendicular to a conductor face.